No, it's not offended. Oh, I see. Weak almost periodicity, you mean? And Roelcke precompactness, whatever. Yeah. Anyway, this is joint work with Todor Tsankov, who will probably be making, who is making a very strong effort to pretend he's ignoring me. Good. Okay, so let me start by something that has nothing to do with the title, almost nothing to do with the title. Okay, no, before starting, I wish to thank you very much for inviting me to the workshop and for this trimester. It's a great thing, very nice, great math. And also to warn you that I'm a model theorist and I'm going to speak about something that's kind of more topological, maybe has something a bit to do with dynamics, and that's odd. Okay, this is going to be an odd talk then. Okay, now let me tell you a story about Vladimir Uspensky, who proved that, let's take G being the isometry group of the Eurison sphere, then this guy is, so it's a Polish group with pointwise convergence and it's minimal. Minimal being there is no weaker Hausdorff group topology on this group. And how did he do this? Okay, I mean, the talk is definitely not about Uspensky's proof, but still let me just tell you a few words. Basically, he put a semigroup structure on the Roelcke compactification of G, and oh fuck, that's not smart. That's not smart. And put a semigroup structure on the Roelcke compactification of G, and if you don't know what it is, it's not very important. I'm going to define things later. And then he analyzed idempotence inside and okay, never mind. Okay, so why am I even mentioning this? Because I want to prove another theorem. I want to talk about the proof of a different theorem. Okay, so the problem is how I state even the theorem. So I'm going to state it in two different ways. So first of all, I'm going to say the following. So let G, maybe I want to write it here actually. I want to keep it this for later. So theorem. Let G be a Roelcke precompact. Again, I'm going to define this in a soon. Well, actually, anyway, let me just state it this way. Let G be a Roelcke precompact Polish group such that, moreover, its Roelcke compactification is equal to its WAP compactification. Well, then G is totally minimal. Sorry. Okay, so what do I mean by totally minimal? I mean, either you know it or if not, it's just something slightly stronger than being minimal. And in any case, I'm going to give an equivalent definition soon enough in our context. So what do the hypotheses mean? That's maybe more important. So topologists here probably know what these means.
Sorry, what does
I'll define this in a second. But for model theorists, I'm going to just restate this. A completely equivalent way to state the hypothesis is to say that G is equal to the automorphism group of a stable Aleph not categorical metric structure. Then G is totally minimal. And the idea was, well, at least parts of the proof are motivated by Uspensky's approach. Okay, so basically I think what it says is, okay, so the formal definition is whenever you have a homomorphism to any Hausdorff topological group, then it's open, a continuous. I think that's the definition. In any case, I'm going to give in a different. I'm going under the assumption of Roelcke precompactness. I'm going to give an equivalent definition, which is the one I'm going to use. So, but basically, it's a strengthening of being minimal. Okay. So I wrote it there so that I can keep it for a while. Yeah, I'm going to say everything. Well, almost. Yeah, just time. But I mean, I'm going to get to the proof at some point. Now I'm actually going to discuss the definitions and the concepts. Okay. So before discussing the definitions and the concepts, there is just this one notation I'm going to introduce, which is very useful. So very often we are going to have so G. Almost all the time is going to denote a Polish group. Sometimes you don't really need that, but let's just assume it's a Polish group, just so that I'm going to add even hypothesis soon enough. Okay, for time being, maybe it's just a topological group, I don't know. Okay, X is going to be a complete metric space. And G is going to act on X. So these are just hypotheses, but they are going to arise all the time. G is going to act on X by isometry, continuously by isometries. Okay, so basically there is a continuous map from G to the isometry group of X. Then I'm going to introduce the following notation. X divided by G is going to be the set of closures. So I'm going to take orbits in X. But the point is I want to take them, the distance between two orbits might be 0. In which case, because it's isometric, the closures are actually equal. So I'm actually going to look at closures of orbits. And then, this is actually a metric space. So for example, okay, that's one thing. Another thing is whenever G is Polish, so it's completely metrizable. In particular, it's metrizable, so it always admits a left invariant metric. Actually, even if it's not metrizable, it always admits left invariant uniformity. So you can actually always form the left completion, but in any case, G hat L is just going to be the completion of G together with this left invariant metric. So I'm going to give a model theoretic interpretation of all this soon enough. But now let's define. So one kind of odd way of defining the Roelcke completion is, but it's going to be very useful for us, this approach, is just to consider that it's G, take the completion, take its square. Now G acts, it's the left invariant, it's a left invariant metric. So G acts isometrically on this. And okay, that's the Roelcke completion of this guy. Okay, definition. G is Roelcke pre-compact if Rg is compact. Equivalent definition. So equivalent definition is if for all open U not empty, there exists a finite F in G such that U F U is all of G. And you can recognize that this condition basically tells you that some uniformity is totally bounded. So the Roelcke uniformity, which I'm not going to define formally, it's uniformly bounded. Sorry, it's totally bounded. So the completion with respect to the Roelcke uniformity is compact, and so that's exactly what I'm saying here. I prefer to define it this way. Anyway, okay. So that's so much for the Roelcke. No, that's not so much for the Roelcke for the Roelcke completion. Oh, I'm sorry. I guess one thing I should have said is the following. The Roelcke completion of G is a completion of G, so it should contain G. So I guess I need to say how I send this guy here. So first of all, if I have a closed orbit, I'm going to write it simply as bracket x. The closure of the orbit of x is going to be noted bracket x. And then if I have an element here, I'm going to send it here to the closure of the orbit of the pair 1, G. So this gives you an embedding of G in Rg. And with this embedding, Rg is the completion of G with respect to the Roelcke uniformity, whatever that is. And G is Roelcke precompact if and only if this completion is compact. Okay, good. The action is, yes, its action is just coordinate-wise. You just act on each. Yeah. Okay. What did I want to say? No, this is all this. So, why would model theorists be even interested in Roelcke precompact groups? There is a good reason. Well, it's not really model theory. It's kind of the combinatorial part, a certain combinatorial aspect of model theory, which is Aleph not categoricity. So, theorem. I guess parts of this theorem were also observed before that by Christian Rosendahl. So G, I'm assuming G is Polish throughout, okay? So G is Roelcke pre-compact if and only if, okay, there are other conditions, but let me just state the important ones. There exists an X, so X complete metric space. G actually acts faithfully on X by isometry, so G embeds, let's say G embeds in the isometry group of X such that the action satisfied, so for all n, Xn divided by G is compact. Now, if I'd written here, if this were just a set, a discrete set, so discrete metric, and so compact would be replaced by finite, and then this would just be oligomorphic. Action is oligomorphic. So this is a continuous version of oligomorphicity. Let's call it approximately oligomorphic. So okay. Now the real nuts. Huh? For all n. For all n. Approximately homomorphic means that, yes, okay. That there are compactly many closures of orbits, very few orbits on all Cartesian powers. And basically, one interpretation, one way of stating at least part of the Riemann-Zevsky theorem is saying that this is if and only if. Okay, there's also a construction for one direction. Okay, but never mind, this is equivalent to there exists M, alpha not categorical. So when I speak about structures, unless I qualify them in metric structures, in the sense that Ward talked about, okay, metric structures, I'm not going to define those. I mean, they're not really going to intervene anyway. But there exists a metric alpha not categorical. So an alpha not categorical structure means a separable structure whose theory is alpha not categorical, such that G equals R. Okay? And of course, as a topological group, so we really this G determines M up to by interpretability, and really, so basically studying Roelcke precompact groups is almost the same as studying aleph not categorical structures, aleph not categorical theories, and there is this interaction is underlying our work, even though I don't know to what extent it will actually be visible in the talk. Okay, good. Oh, what this means, for example, that it's really easy for us now to give examples of, many groups for which people either as themselves or have shown that they were Roelcke precompact or that they were not Roelcke precompact, basically are given in terms of automorphism groups of metric or classical discrete structures, and now this tells you exactly whether this gives you a criterion to showing that they are Roelcke precompact. So, okay, isometry of U1, automorphisms of Q with the order, linear isometries of the Gurari space, all these are Roelcke precompact because the structures are known to be alpha not categorical. Polish group. G is a Polish group. Polish group. The metric doesn't matter because any two left invariant metrics are equivalent. So really, it's actually more about the left uniformity, which is unique. But I don't. It's not so easy to show that it's not Roelcke precompact. Well, showing that something is not Roelcke precompact is. Well, you need to show, no. Yes, because actually there is another criterion here, which I omitted, which says, which says that this is if and only if, whenever you have an action on X, such that X over G is compact, then X to the n over G is compact for all n. And now, for example, how do you show that the automorphism group of the full Urison is not Roelcke precompact? Okay, one way to say is that this is not an aleph not categorical structure. So that's, but it is, okay, no, that's actually not a proof. But the other way is to show, look, the x over G is a single point, but x squared to the G is not compact, so it's not Roelcke precompact. Okay, sorry, so, but I didn't want, I was hoping to not to say that. Anyway, so that's a very crude tool for at least showing that something, fairly useful to show. Okay, you can show that lots of things are Roelcke precompact. For now on, we are just going to assume G is Polish and Roelcke precompact. Okay, I'm adding this to my hypothesis. Okay, so now let's remember what. Okay, so Ouspensky, I raised Ouspensky, but still, what did he do? He put a semigroup law. He put a semigroup law on this thing. Okay, so when does Okay, so on part of R, there already is a law, the group law on G. And when do you can put a semi-group law on R? And this is actually a badly stated question because I'm not really, I mean, if you don't make any additional hypothesis, it's kind of really difficult to answer. So actually what Ouspensky did lies in the bad case. But it's in the bad case, but something else happens. But if you really want this to be canonical, so you want this to extend this law, you want it to be unique modulo extension of this law. Now G is dense in RG, so you might want the group law to be continuous. Okay, that's actually too much, but it's actually enough to be just separately continuous. Okay, so that's a semi-topological semi-group law. Okay, and with this question, this is a well-stated question. If it exists, it's unique. And the answer is if and only if. If and only if. This is the well-known fact. If and only if RG equals WG. So the WAP compactification of G. So I'm actually not going to talk much. Will you
tell us what WG is?
Maybe. Well, I'm going to tell you one thing. I mean, there is a formal definition that I don't want to introduce right now. I might tell you. I might tell you later. Maybe I might tell you later. All I can tell you now is that usually in the general situation, what you have is that WG is always a quotient of RG, and it's the maximal quotient on which you can extend. The law here descends to a law here, which actually, the law on G. So it's a map from, in particular, you have a map from G to WG, and the law of G can extend to a semi-topological, semi-group law on WG. So there is a maximal quotient of RG on which that's possible, and that's WG. That's one definition. It's an angled definition, but it's a possible definition. And then, so RG equals WG if and only if this can be done here. Okay? Yeah, so let me give you another. Let me give you.
That you gave is exactly what.
Yes, so let me give you another definition. Let me give you another criterion. No, I mean, I agree that this is kind of tautological, so let me give you another criterion. Okay? This is better?
Yeah.
If and only if M is stable.
At least now.
Yes. Yes, in terms of types in this structure. Yes, it's possible. I'll get to that later. It's a question of time. I actually want to talk about the theorem. If I have time, I'll talk about that. That's my last. Okay. So basically, R of G equals W of G if and only if G being the automorphism group of M, M is stable. And of course, if I can write G as an automorphism group of M and M prime are bi-interpretable, so one is stable if the other one is stable. So that's clear. I mean, that's well defined. Okay. I might actually get to the formal definition of WG later if I have time. Okay. Now, sorry. My notes tell me that I actually need to tell the model theorists something right now. And, sorry, I'm actually answering, sorry. My notes tell me I should answer you right now. So let me. Okay, so first of all, G is a group of automorphisms from M into M. Okay, so I'm fixing, now I'm working in this situation. So G is just automorphic, so it's M isomorphic with M. Okay, so what is the left completion? If you think really, really hard, you see that this is exactly all the elementary embedding of M. Of M into M. Okay, so basically these are all copies of M inside M, but not as sets, as really as enumerated. So you fix, let's think that we fix an enumeration of M, or if M is uncountable, it's separable. So let's fix an enumeration of a dense sequence in M. So let's fix it. So let's fix some Xi, and let's fix some Xi in M to the power N, which enumerates a dense set, and then these are just G hat L is just all copies of Xi. I mean, all automorphic copies, or all guys with the same type as Xi inside here. And then if you think about what RG, okay, here, let's look at that definition. Think about this for a second. What it tells you is it's just all copies. So RG is now all sets of types of, let's say, X and Y, where X has the same type as Y, has the same type as C. Or if you wish morally, it's all the types of M1, or possibilities for how do you place two models, one with respect to the other, M1 and M2, where M1 is isomorphic to M2, isomorphic to M, but you should really think about these as enumerated models. Okay, so what about, so now I'm going to explain to you, at least partially, why this corresponds to this. I guess at some point I actually need to, oh, wait a minute. Actually, I erased what I wanted to, never mind. I thought I'd erase Uspensky, but actually I erased my own theorem. Okay, so assume I have 2 points so assume I am stable, okay? Assume we are stable, and we have 2 points P and Q in W equal R, okay? So that's, let's call this is a type of M1, M2, and this Q is the type of say 3, M4. Okay, but the point is I can change those. I can just, as long as I keep the type, I can change them. So I can actually say that, let's say that M3 is actually equal to M2, and moreover, M1 is independent over M2 from our M4. Well then, this uniquely determines the type of M1, M4, which is P star, or P times Q. Okay? So stability naturally induces, and if you think model theory, think about what you learned in model theory, this law is it continues separately, but not jointly. Okay, and a lot of that. Okay, but I hope at least I partially convinced you of that. At least partially. And I guess I could say, okay, in a parenthesis, that when this is not the case, when it's not stable, that basically WG is the quotient corresponding to all stable formulae. So it's a quotient. You lose information. Okay. I hope I answered at least some of the questions. Okay. Oh, yeah. What it says is WG is the maximal quotient, la la la. So if you wish, it's the spectrum of WAP G, which contains of the formula, but okay, let's just forget it. Okay, so now let's get to the proof of the theorem. Let's get to the proof of the theorem. So the argument. So again, recall, I have G is Roelcke precompact, and RG equals WG. Equivalently, G is the automorphism of something which is Aleph naught, categorical and stable. And what I want to show is that it's totally minimal. So first of all, a small lemma. Just with this as hypothesis, G is totally minimal. If and only if every Polish quotient is surjective. So I guess I should say what I mean by quotient. It's not exactly, okay. Every Polish quotient of G is surjective, where by quotient I mean is a map pi from G to some G prime, continuous and dense image, with dense image. Okay, so this is not, this is, so this is just, my space is limited somehow. So this is not too complicated, and we might as well just take it as a definition. Okay, so we need to show that every Polish quotient of G is surjective. So how do we go about this? So, okay, so let's consider a Polish quotient. You know what? Let's just consider this Polish quotient. Okay, so G goes to G prime. Okay, this induces, just by the universal property of the WAP compactification, a map from WG to WG prime. So there is, you can define WG also via a universal property that gives you exactly this. So take the identity here. So one of G prime, so this is contained here. This is, actually it's not really contained, it could be a quotient, but there is a map here, there is a map here. And actually, once you add the hypothesis that this is stable, that this is R equals to W, then this actually is an inclusion. So let's just say it's an inclusion. Take this guy and pull it back. Okay, so if this is pi, let's call this pi bar. And take pi bar inverse of 1 of G prime. So this is a sub-semigroup of this guy. Okay? It's a sub-semigroup. Call it, what call it? Call it S. Okay? Call it S. This is a sub-semigroup of this guy. And so here's the first odd lemma. Of course, it's a closed subsemigroup, so it's a compact subsemigroup. So the first odd lemma says that, well, if S subset of WG is a closed semigroup, yeah, I guess maybe we need, do we need to assume that one is there? At least, and then the hypothesis of this. Okay, I don't remember the exact one. Let's just, okay, maybe I'm mistaken. If I'm mistaken about the hypothesis, in any case, all the hypotheses hold for that S, then there exists a unique idempotent E in S, which is minimal, which is it's unique, so it's least with respect to W and some ordering I'm going to define now. So what is this ordering? So this actually has, I mean, in the same way that W has a model theoretic interpretation as types, and the law on W has a model theoretic interpretation as independence, via independence, this ordering also has a model theoretic interpretation. It's actually just the fundamental order. I mean, the ordering on types is just the fundamental order between types. French school stability. I mean, it's true. I mean, that's how we got there. And I mean, the point is that, okay, I guess I should have told you in the beginning that there is an entire story here you don't see. Basically, what I'm giving you is there were many model theoretic arguments that ended up being transposed. I mean, so the ideas, many of the ideas came from model theory, then transposed to purely topological arguments, and then the model theory is no longer evident at all. But the interest in looking at this came originally from the fact that this is just a fundamental order in that sense. Okay, so how do we define the fundamental order here? It's, so I say P is smaller than Q if W times P is contained in W times Q. Okay, that's stupid definition. Okay, but so okay, so once you get there, I mean, this is an extremely natural definition in this purely topological context, but it has a very strong and well-studied model theoretic meaning. Urysohn case is very unstable. There is nothing stable there. No, so in Urysohn space, W of G is trivial. So it's completely non-illustratable on the Urysohn case. Oh, sorry. What I should have said also is that this presentation also allows you a quick and easy way to calculate R of G for a copy compact G if you understand the structure of each G's automorphism group. Okay, just a side remark. So that's kind of side results that basically it's easier to prove or to calculate if you have some model theoretic understanding of various structures. Okay, but this is not my main aim. Okay. Moreover, okay, so I'm here. Okay, so my S, so assume I have a closed subsemi group, and maybe it satisfies some more hypothesis. For example, maybe it contains also one and stuff. Okay. Anyway, I'm not sure what that's needed. Anyway, in any case, it contains a point which is list. If you think about this in terms of types, it contains a type such that M1 and M2 are as independent as possible. But in addition, that it's an idempotent. So I'm going to get what the idempotent.
Do you actually really need to assume that it has a two-sided idea, not just a subset? Because this one is.
Yeah. Okay. So I'm not sure what. Okay. So this is okay. Whatever. Just for this. Okay. Okay. With this S. It's true. I don't remember. I don't remember what that was in this one. I mean, once you have the right hypothesis, the proof is actually very easy. It's just zone and then some calculations to make sure. I mean, zone to show that there is a least class, and then to show that, okay, zone to show that there is a minimal class, then you find the idempotent. The argument is very easy, just need to get right about this. Okay, okay, and moreover, since I erased this stuff and I'm just using the S there, this S is normal, and since E is uniquely determined, my S means that E is central. Okay. So we have a central idempotent, which code at least a part of our problem, and okay. So what I'm going to do with this idempotent? Okay, let's write it here. So I'm taking this E, and I'm going to define H of E as a set of all H in W, such that, first of all, HE equals, okay, HEV equals, obviously equals EH, so that's not very important, equals H. So they are not, they don't lie above E. Basically, it means they lie below E in the fundamental order, and they actually lie exactly together with E in the fundamental order. So H star. Oh, I guess I should have said what. I mean, star is just take inversion. Star exists both on R of G and on W of G. It's just the continuous extension of inversion. So it's not an inverse. On W of G, it's not an inverse for the semigroup law, but it's the unique extension by continuity of inversion on G. And we are asking that here, it actually is inversion. Okay, so basically, it's actually a quotient. This is a quotient of G, because you can write a map. G goes to H of E, just sending any G to G times E, which is the same as E times G, actually. And this is going to be dense. This is well defined. It's going to be dense here. So in the sense of quotient I gave earlier, this is a quotient of G, or this pi E. Okay? And now, okay, so now, this is all, I mean, okay, so now I'm talking as a model theorist. I'm sorry. Now I cannot avoid talking as a model theorist, as the intuition of a model theorist, which says that all this stuff is about independence. This E is about most independence way to put two copies. Okay, basically, it means that there are two copies of M which are independent over their intersection, and moreover, because I want this to be idempotent, I want this to be well defined, the intersection has to be algebraically closed. Oh, well, no, the intersection is always algebraically closed. But okay, and the intersection is always algebraically closed. And basically, there's some algebraic closedness that comes in, which doesn't appear in the Eurism case, because in the Eurism case, the algebraic closure is trivial. But there is some algebraic closure mess which comes in, and which independence cannot see, because everything independence sees, in a sense, everything is already algebraically closed. So this is going to miss a part. Okay, so here's another lemma, which is not, okay, so here's a next step in the proof. So let's forget this for a second, and let's concentrate on this. Recall where I started. I started with a quotient, G going from G to G prime. And then from this quotient, I got this E. And E got this entire thing up to something compact. This is actually equal to H of E divided by K, where K is normal and compact. Okay, in particular, this means that this map is surjective. Oh, and the composition and the entire composition is pi. Is the pi I started with. So I really don't have to worry. Oh, excellent. So I really don't have to worry about this part. This is surjective. So the only question is, last thing to show is that this is surjective. I want to show that the composition is surjective. I know this is surjective. Let's show that this is surjective. Okay, so we still need to understand central idempotence in a way that's actually not that different from, I mean, this step over there, the one on the right, didn't exist in the Ouspensky case, and now we need to look at the part on the left. And, okay, the situation is different, but in any case, let's prove the following. So the next step in the proof is the following, so proposition. So say E in W, so W is always W of G, I'm just being lazy, which is equal to R of G. So assume this is a central idempotent. And let's define the following thing. K is the set of all P in W which are actually swallowed by E. So if you think a bit for a second, G intersection K is exactly the kernel of pi E, of that guy. Okay, so in particular it's normal. Let's call it N. Well, but then what we say is that N then N is dense in K. And from this, it's actually, once you have this result, it's actually not that complicated to show that that H of E is exactly G divided by N, and you got your surjectivity. So maybe I want to say something, and okay, so once you use this to show this, and then you're done. The theorem is proved, because this is surjective on this, which is surjective on that. So maybe I want to say, I mostly actually, yeah, I have a few more minutes. I don't want to get into details of any of this from the topological point of view. Some of these proofs were basically figured out by a model, take a model theoretic argument, so translate this to model theoretic setting, then the theorem is, well, okay, I know it's true, and then very carefully unwind the translation. So to get back to a purely topological argument. So for example, this one, model theoretically, it's proved by a chain, an elementary chain argument. So an elementary chain argument translates, in this case, to a Baire argument. And actually, then the proof is quite easy. Okay, there is the lemma here. It's not that easy. Okay, it's the easy modulo lemma, which is, each step in itself is easy. But somehow the juxtaposition of steps really comes from a model theoretic, model theoretic understanding of what this is. So maybe I want to end this talk by giving a few additional words about what it means, what all these notions mean model theoretically. Okay. So again, I'm assuming that W is equal to R, so we are talking about a completely stable situation. If not, things don't work that well. Or, some of these things work, some don't. Let's just ignore that case. Okay, so first of all about this, I told you that this is, I told you that this was a fundamental order. Maybe let's just make it slightly clearer. So I said if this is, okay, so let's write P as a type of M1, M2, and let's write Q as a type of, I guess I can, for the first one, I can take also M1, so M1, M3. Okay. Now M2 and M3 are both enumerated, there is a fixed enumeration, so M1 in itself has the same type, with the enumeration of M1 has the same type as the enumeration of M2, has the same type as the enumeration of M3. And within that type, I have, so if and only if, I have a fundamental order, if and only if the fundamental class of the type of M2 over M1 is, okay, now it's just a question of how do you put more independent is bigger in the fundamental order or smaller in the fundamental order? Bigger? More independent is bigger. Okay, then it's an order reversing. Okay, whatever. This is freer. this is freer than this is just a fundamental order on types in that complete of types with parameters in that complete type without parameters. So that's one thing I wanted to say. And then actually there is a lot of algebraic calculation. For example, there is just a cute result. For example, if you have, let's say you have P and Q in W, and you know that, okay, you know that QP, so you know that QP is going to be smaller, just by definition, is always smaller than P in the fundamental order, because just look at the definition, it's clear. If they are equal in the fundamental order, then, or they're equal in the fundamental order, if and only if P actually equal to Q star QP, which is a very odd way of saying that if you have a type and an extension of the type to a larger set, then this extension has the same fundamental class if and only if it's the unique non-forking extension to that. So maybe that's not quite clear, but that's exactly what this says. Okay, so a lot of, I'm just saying that just in order to say that there is a lot of independence, what model theorists are used to express with. If you so Q times P. No, I'm not answering the question. Sorry, P times Q. Yes, P times Q. Well, then you don't even have this a priori.
So this is a different order than the orders.
Yeah, because okay, no, because you're working over. I mean, you just need to fix which side you are working over, and then work over that side. Otherwise, I mean, everything is, of course, it can be symmetrized, but you need to fix a side. So that just way to saying that what we model theorists call independence calculus can actually be, in many cases, just be restated in purely set of algebraic identities in this context, which is very cute, and it's underlying a lot. I mean, I omitted all the details, but a lot of this is in the details of everything I said. And the last thing I want to say, because I have a few more minutes, is say something about idempotence and about these propositions, just because I like it very much. Well, I like it very much. This was the part that took most effort to translate from purely model theoretic statements to topological statements, because somehow that's where okay, just took most, okay, whatever. But what does it say? I mean, okay, look, what does it mean to be an idempotent? I guess I said it earlier. I mean, you want M, so idempotent is the same thing as saying that I have M, so is the type of M1, M2, which are actually independent over the intersection, and the intersection lies in the same way in M1 and in M2. So if you compose now with another guy of this form, so you have, okay, let's write it more like this, and now I compose with another guy, so now these two guys are independent over this, and now by model theoretic independence calculus, you just see that these two guys are independent over the intersection. It's always the same intersection, so E times E equals E. Okay, so idempotent is exactly this kind of situation. When is it central? So let's call this A, this intersection, let's call it A. So now I have M. So basically idempotents are just a way of coding algebraically closed subsets. So it's the same thing as A in M, algebraically closed. So now, when is an idempotent central? Well, if I cannot move A, namely if A is empty set definable. Okay. If A is invariant other automorphisms, if you wish. And then this density argument, what does it actually say? What is the corresponding model theoretic statement? It's actually a model theoretic statement that is not very difficult, but actually does require a proof. I mean, I assume that model theorists here are going to say, yes, we know that. I mean, of course, I mean, it's not that complicated. Basically, what it says is the following. You have M and you have A, and you have these 2 points here, say A and B. And you only know that the type of little a over big A is the same as the type of little b over big A, okay? So type of A and B are the same over A. Then, there exists an extension, an elementary extension. So I take an elementary extension. And okay, in this elementary extension, of course, I have to extend A because A is a definable set. So there exists a bigger set, a bigger model N, such that there exists a G in the automorphism group of N, which fixes A, but A as interpreted in N, sending A to B. So this is in classical logic. In continuous logic, you would have to say G sends A arbitrarily close to B, and okay, whatever. So I guess maybe it's kind of difficult to see. Well, maybe you can see the relation. I mean, I hope I gave you at least the ingredients to see the relation. But this is exactly the same statement as the one written up there. And what? And yeah, okay. So a lot of the work here was you needed to understand that idempotent, understand what it means to be a central idempotent. Oh, that's what it means to be a central idempotent. Oh, okay, that's the model theoretic result we need. Now, how the hell do we prove it in purely topological terms? And okay, whatever. I guess that's a good time to stop. Thank you. No. Bounded Urison is not stable.
Okay. So what concrete groups do you get as strongly minimal from that?
Any automorphic group of stable. So okay. So obvious thing like unitary group, isomorphism group of the probability space, isometry groups of any. Totally minimal. Yes. Totally minimal. Yes. No. No, their W is not trivial, but it's definitely not stable.
Other examples? The examples you cited were not examples of the theorem, are they? Are there historically prior examples of the theorem?
This you should have to ask a topologist. Is there a topologist in the?
Another question that may be strange on the spot, but there's quite a bit of machine reducibility here. Do you ever actually use the symmetry of independence?
The symmetry of independence. I guess it's somehow it's probably implicit in the sense that. Yes, it's implicit. Well, I mean, I'm not formally using it, but it's implicit in the fact that if you take P times Q and you take its inverse, that's the same as Q inverse times P inverse. I mean, that's symmetry of independence. So again, forking calculus to algebraic identities.
Now, I've heard that there is some kind of rudimentary independence calculus in the Universality space.
Oh, yeah, okay. So I guess, okay, I'm forgetting. That was something I actually intended to say. So how did Ouspensky get his semi-group law? He actually did use a notion of, he actually did give exactly the same definition for a notion of independence, which is not a stable notion of independence. That's just, you have two metrics, you have three metric spaces, or you have a metric space X, which embeds in Y.
So when I'm asking whether the Pantz-Ziegler formalism is at all relevant here. That there is a formalism. Yes?
Oh yeah. You mean of notions of independence, or?
Yeah,
That's the next. Okay. So what I'm saying is that Uspensky could. You can definitely express Uspensky's semi-group law in that formalism. That's definite. Of course, the stable case can be expressed in that formalism, but then you're using other properties of stability. We are using a lot of it. So, in Uspensky's argument does use an extremely weak form of continuity of the semi-group law, which definitely doesn't characterize it, but I think is a consequence of this formalism, of the fact that it comes from an independence notion with this formalism. But then there are lots of other ingredients which might be missing. So I definitely don't think that, I don't think I can say just, okay, if you have any notion of independence weak like that, then it's going to work just as well. But it's definitely something that's worth looking at as well in the near future. Okay, but yes, it's not covered by this.